Okay, so hello everyone, welcome to our webinar. My name is Daniel Jędrzejczyk. I am a senior software engineer at Codilime.
And my name is Artur Jaworski. I am a senior software engineer at Codilime as well.
Today we will talk about FPGA in the cloud based on our project where we offloaded eBPF functionality to external device. By this presentation, we would like to give you some understanding about the challenges and opportunities which you may meet if you are going to work with FPGA-based devices. We will tell you about what tasks needs to be done when working with FPGA. What are the advantages of using FPGA? Is it possible to use it in cloud services? Then based on project we have done, we will go through the items which are need to create all necessary deliverables to run new device. If you will have some questions during the presentation, please put them into questions and answer panel. We will try to answer them at the Q&A part. Artur, could you tell us why we should even consider offloading?
Yeah, so let's talk about why we should even consider offloading, and especially we'll focus on why we should consider offloading on FPGA devices. But let's start with a brief reminder or for some people introduction to the goals of offloading in modern systems. So for simplicity, let's take a look at two main aspects: the facilitation of the CPU and the acceleration of operations. So in modern data centers, such as private or public clouds, a CPU is viewed as a sellable resource. It is shared among different VPSs. On the other hand, for the cloud users, the CPU is a resource that they pay for. So each opportunity for optimizing the resource usage can be lucrative for both groups. With the offloading, we can save CPU time by outsourcing tasks from the main CPU to the other hardware. We can also aim to accelerate those operations. The best example here would be offloading and acceleration of 3D or AI tasks to the GPU. CPU is a powerful and flexible beast, but its universal approach is a trade-off. For years, the approach was if something is too slow, just buy more computing power. But there is a limit to this approach. In last years, we have seen a shift in this mindset. A lot of people are looking for dedicated hardware, either for better performance or lower power consumption. And to achieve that goal, we can use a different type of hardware. The choice of hardware really depends on the use case we are aiming for. We can use ASICs, which is a dedicated hardware tailored for specific use case, and also it gives us the best possible performance. Those specific use cases can be like, for example, a classic network card. It handles the physical connection with a medium, with a cable, but can also include the acceleration part, for example, for network protocols like VLAN or MPLS. We can also choose a GPU as our accelerator. The GPU will be helpful in all those scenarios which involves parallel computation and lots of data. Like I said before, it can be used for tasks like 3D rendering or acceleration of artificial intelligence. And last but not least, we can use the FPGA. Its offer performance, which is similar to that of dedicated hardware. But it is programmable. It can be used in the variety of tasks, like real-time computer vision or specific ones, like analysis of DNA sequences. It is worth to note that FPGA-based SmartNIC showed that FPGA can also be used to offload networking infrastructure for reduce latency and to deliver better throughput. And now let's take a look at the advantages of using FPGA.
Yes, among many advantages of FPGA, we would like to point you some. We can treat FPGA as a wildcard. It might be any device we are able to describe using hardware description language. Such device will be almost like dedicated hardware. I am emphasizing almost because FPGA's flexibility has its price. Generic character of digital blocks is not as fast as dedicated hardware blocks, but for sure you will feel the difference comparing with some software solution. We don't need to prepare additional hardware, like extension cards. There are already companies which prepared PCI Express card with FPGA surrounded by different peripherals. We may focus on device functionality instead of wondering power or temperature distribution on the board. We may check if our device is worth making as specialized integrated circuit. If our proof of concept device runs well on FPGA, we may expect even better performance when prepared as a specialized integrated circuit. Preparation of ASIC is as easy as sending files created during synthesis of our HDL sources to integrated circuit manufacturer. Simple reconfiguration. Uploaded firmware defines the functionality of our FPGA. In traditional hardware, we will need to manually change extension card or integrated circuit. With FPGA, after a configuration, we get completely different device. Data processed inside FPGA is separated from the main memory and processor. It gives less possibility to access main memory or directly influence on processor behavior. We are designing boundaries of our device and limiting its access by hardware. So what do we need to get our FPGA to work? We will for sure need a firmware, an FPGA configuration, something which defines the behavior of our device, and the drivers, usually specific one, because our device will probably not use the standard interface. Is it worth to mention that firmware match only to target FPGA model and cannot be exchanged between smaller or bigger devices? Artur, is it possible to use FPGA in the cloud?
It looks like we can use FPGA in the cloud. Right now, lots of providers have some kinds of accelerator in their offer. Often the list ends with the GPU, but not always. We decided to use Amazon AWS, which offer instances with FPGA. It is also worth noting that Amazon also offers development machine dedicated for their environment. It contains all necessary tools for development and deployment. It contains things like licenses for firmware synthesizer, for firmware synthesis, and other useful tools. And we think it's a really cool thing. Using FPGA in the cloud can open a whole new world of possibilities. For example, if you are a provider of a video conference application and you are hosting it in the cloud, you can use this FPGA hardware to enhance your application with, for example, speech-to-text algorithms. Also, environment like this slightly reduce initial cost of the technology adaptation. But let's take a step back to the common architecture of FPGA solutions. For both a local system as well as a cloud one, we have necessary parts which needs to be developed for our FPGA. We may divide architecture of FPGA solution onto two parts. The first one would be a hardware part, which is like Daniel said before, it's a configuration of the DPDK of FPGA and HDL code, which implements our custom logic, and software part, where we'll handle communication, data transfer, and signaling with our FPGA. Because after all, FPGA allows us to create custom circuits, and handling those custom circuits also needs to be custom. In our case, in case of Amazon environment, the bridge between those components is a PCI Express bus. And Daniel, could you tell us more about the communication between those two components?
Yes. In Amazon framework, we can recognize few functional parts responsible for different tasks. First of all, it is a shell. Shell is responsible for management of PCI Express connection, external memory access, recognition of device on the system. It also provides AXI interfaces to our custom logic. AXI stands for Advanced Extensible Interface. It is an on-chip communication bus protocol. It specifies signals which controls data flow between digital blocks. Another part is custom logic. This is a place for us. Here we shall place our idea, our design. The drivers. Most of the PCI Express related items are done by hardware, but some specific drivers, like streaming data packets, are already prepared by Amazon in DPDK. We may use them to build more complex devices, drivers. Application. Here we may put our logic. Usage of DPDK framework allows us to use, for example, test PMD application, almost from the shelf. It is already, we just need to reach for that. Only few additional arguments pointing to our driver, and we may set up environment which will route data from network or files to our device. That was a theoretical introduction. There is no better way to recognize the device than prepare some project with it. So let's take a closer look on what we have done for recognition of FPGA in the cloud.
Okay, so we decided to offload eBPF. eBPF stands for Extended Barclay Packet Filter. This is an approach for network packet filtering in Linux kernel. It is used by many projects, for example, by Project Cilium for Kubernetes or by Netflix. The filters are realized by running special eBPF programs. eBPF has own set of instruction to simplify development and stability of code, which is run in kernel space. eBPF filtering is happening. It's worth to mention that eBPF filtering is happening before packets enter the network stack in a kernel, because it may facilitate network stack from dropped packets. And offloading this eBPF may further improve the performance. If you are interested more about eBPF, you may check presentation done by one of our colleagues. The link is in a QR code and also is available in resources of this webinar. So Daniel, could you tell us why we choose eBPF?
Yes, mainly because it is not trivial functionality. Amazon has already some example FPGA projects prepared for special data processing. We wanted to offload a real kernel functionality, and eBPF happened to be a good candidate for it. Core functionality of eBPF lays in special processor emulated in kernel, which understand own set of instructions. For our hardware solution, we used hBPF project, which implements eBPF processor as a softcore. By softcore, I understand processor designed by processor described by hardware description language. hBPF projects were created with use of LaTeX. LaTeX is a Python-based library which allows us to create some object relations, and based on that, it generates HDL sources. Such approach in FPGA world is called high-level synthesis. High-level synthesis is a concept where we are describing algorithms in different programming language and translate them into HDL. This allows to reuse existing algorithms written in software languages in hardware world. Unfortunately, this is often not easy task. Code needs to be adjusted by additional description, but more tools start to support this functionality. Another advantage of high-level synthesis is if an engineer better understands software languages than HDL, he may develop a project in his favorite language, making him easier to understand hardware. LaTeX, with its dependencies, do not need additional licenses. It may be run on any workstation. After LaTeX generates HDL sources, we may do first checks. We may use sources with HDL simulators like Model Sim or LaTeX test suite and confirm desired behavior. When initial tests looks promising, generated HDL files may be copied into our custom logic part. Then we need to move to Amazon development machine. That development machine has all necessary tools and licenses to synthesize a configuration bitstream for our FPGA device. Be aware that FPGA producers has own business model where they are licensing their tools. In Amazon environment, we don't need to worry about it. We already paying for that by renting their machine. In this stage, we may got an information that prepared HDL may not be synthesized. It may mean that there are no resources on the device which allow us to configure desired behavior, or the tool could not handle sources we gave it to process. In such case, we need to go back to LaTeX or to HDL and adjust description. After synthesis, result bitstream were moved to Amazon S3 bucket. S3 bucket is an Amazon file repository. After S3 bucket reprocess the bitstream, we deploy F1 test machine. On test machine, we run test PMD DPDK application to check the behavior of our BPF device. On this stage, the test PMD understand additional arguments with eBPF program because of our driver. Also allows for accessing debug registers we put into hardware part to verify desired functionality. Maybe let's take a closer look at how the data flows in our project. This is a simplified view of our device. Test PMD application additionally gets argument like eBPF executable with BPF program, input pickup, which is the file with test packets, output pickup with which store the processed packets. eBPF executable is created by compiling C source code for eBPF platform. This is the same code used in kernel solution. Initially, our application sends machine code extracted from BPF executable to hBPF program memory. Then opens input pickup file and sends data packets to hBPF data buffer. Data control flow on PCI Express bus is done through shell by setting not ready signal on AXI bus. hBPF softcore during filling the buffer is in reset state. Reset is released after packet is transferred to data buffer on our FPGA. Then hBPF starts to execute its program. When finished, processed packet may be dropped or forwarded back to host. When dropped, next packet is allowed to be transferred to our buffer. When processed packet shall be forwarded back, entire data buffer is sent through AXI-bus to the host. TestBMD application captures all sent back packets to output pickup file for later verification. If you are wondering what else could be done, our project creates the base for further investigation. Dependent from the areas which will interest us the most, it may use more than one instance of hBPF. It will allow to process multiple packets simultaneously, like in GPU. It may use multiple PCI Express queues to feed those multiple instances with data. It may directly communicate with network card through direct PCI Express transactions without CPU involvement. Let's now briefly summarize what we talk about.
Okay, so by this presentation, we wanted to show you that first, the cloud providers have other accelerator than popular GPUs. And next, usage of FPGA in the clouds really opens new opportunities which were limited to on-site, on-prem solution before.
We are able to recognize usage of different hardware approach in easier way by simple reconfiguration instead of manual exchange of the device. We don't need to design entire hardware. As a first step, we are able to recognize a potential of new hardware designs. High-level synthesis approach opens hardware area for engineers which are experts in other than HDL languages and reuse of existing data processing algorithms. If you have some questions, you may put them in question and answer panel. We will try to answer on your questions now.
Okay, it looks like we have the first question. So can the hBPF hardware module handle multiple calls? I think previously we did some testing about if it is possible. Theoretically, it is possible so to have more than one instances because we talked about it previously, but I don't think we already there. It's a thing for the future.
Yeah, so actually currently our project is, let's say, single threaded. So one packet comes, processor analyzes it, and then send back the response. And actually, probably the question refers to that if we are able to process more packets simultaneously. So this is some open item here. And actually, we checked that the FPGA should handle 3 instances of hBPF. So actually, three multiple calls could be processed simultaneously. Okay, the next question is,
how long does it take to synthesize entire project?
Okay.
It is like I think because synthesizing this project is there's building the whole project is divided into few parts. First, it is the LiteX, which I think took
a few minutes,
like 5 minutes or something. It generates the HDL code, which
then we are moving to the development machine.
Yeah, we need to synthesize it into the like intermediate representation. And after it took, I think, 1.5 hours. The next, it is sent to the S3 bucket. S3 bucket also do some magic with it, and to prepare it for Amazon AWS environment. and it's I
It
think
takes-
took 1 hour
Yeah.
additional. So we are talking about 2.5 to 3 hours of the whole building. Okay. So next question. I have noticed that Amazon F1 is a bit stale in terms of new designs. It is still a viable platform.
Mhm.
I don't exactly understand what is in terms of a new design. Do you have an idea?
Okay. So
Maybe new models?
maybe author means that that the model of FPGA is getting, obsolete. Okay, so it's hard to say. Actually, this is something what Amazon has in their offer, right? So right now we are able to run create the instance of the server with this device, and actually we are able to use it. There is also a lot of project there and the tools supporting that. So I would say that for this very moment, yes, this platform is actually ready to use.
It probably isn't the most powerful FPGA on the market, I think, but you don't always need to have the most powerful FPGA. It really depends on the use case.
I think that they varies the platform because they have in their offer smaller and bigger models, right? So actually, if you are missed about some resources, you could always reach for the bigger one. I think we use the smallest, right? Because it was the cheapest, right? To rent the machine.
Okay. Hi, DPDK PMD driver is running in user space, but eBPF is a part of the kernel space. How are they working together? Okay, because we are here talking about hBPF. So we took a project hBPF, which is hardware BPF, hardware implementation of eBPF, and we integrated it with Amazon framework. The PMD here is responsible for communication through the PCI with with this FPGA, with our hBPF on the FPGA.
That's right. That's right. And actually, they are need to work together, right? So this is something completely separate. The packets are filtered before it enters the network stack. So when we create with our TISPMD a routing of the data, which firstly comes into our device, our FPGA, and the outgoing packets will go back to the kernel, right? We still are able to run eBPF on the kernel, right? Because this is happen in the steps, right? So the packets which enters firstly to our server are processed by FPGA and maybe processed by the kernel, but this is not necessary. So they are not cooperating. This is completely different place.
Okay, follow up. I think it's a follow up about can the hBPF hardware module handle multiples call? So follow up. If not, we are serializing the hardware, which is not efficient. I think it really depends because if we are going with the soft core, it can be not super efficient. But if we switch our mindset to, I think, FPGA, where the lots of things can happen not simultaneously, but like parallel.
So actually, yeah, eBPF is a portion of emulated processor. Yeah, so we are doing the one instruction after another, but please keep in mind that eBPF in kernel is not the virtual machine itself. It is, let's say, some kind of interpreter. It takes the instruction and jumps through the instructions, doing what the instruction shall do. So in this case, the FPGA will be actually will do it faster because it is clocked by the clock, and the GTL logic is doing the operations, right? Yes, and in kernel you will need each operations will need through machine cycles to process and actually to put the data on it. So it may be more efficient, and especially when we will add the parallelization, right? Because on the CPU, okay, you can always run on multiple processors. Yeah. But you are wasting then the processors.
Also, I think it is worth to note that we have done it as a proof of concept. Like, we didn't test the performance. We didn't do a side-by-side comparison between eBPF and hBPF. With this webinar, we would like to give you some insight what is possible. Like before, because previously when we was thinking about FPGA, was only thinking about the on-prem solutions. Mm-hmm. Like, but with this approach, like I said before, it opens a world of possibilities. Like, I think the most popular example here is like a lot of universities use it for DNA sequencing. There's already a solution for it to run the algorithm sequencing DNA and proteins on Amazon F1. Mm-hmm.
Okay.
Okay. Thank you for information.
We will take a look at it.
Okay, I think we have answered all the questions.
Yes, so that is all what we have for you today. If you remind yourself some questions later, please do not hesitate to ask. You can reach out to us through our email, team@codilime.com. Thank you for your participation today. Please stay a few more minutes and fill the survey regarding our webinar after it will be closed. So
goodbye.
Thank you. Goodbye.
Thank you.